Good morning and welcome to AIST Decarbonization Webinar starting at 10 o'clock East Coast time today on Tuesday, the 25th of April. We're very glad to have you sign in with us today. We are in the process of receiving somewhere close to perhaps 200 people that are registered from 25 different countries. This webinar will be available in its recorded form in the future, and slides later in this webinar presentation will show you where they are found. My name is Charlie Bender, and I am the staff engineer here in producing this webinar from Pittsburgh, Pennsylvania. Our moderators are coming from Canada and Germany, and our presenters are coming from 2 different states here in the United States. The presentation is Decarbonization, the Evolution, Metallurgy, and Operational Experience of EAF and SAF Steelmaking. It is organized by AIST's Decarbonization Subcommittee of the Energy and Utilities Technical Committee. Several guidelines for AIST webinars. Attendees' audio have been disabled. Questions to the presenter should be submitted via the question and answer feature of this software, which you will find at the top or the bottom of your screen. The host and the moderator will determine which questions are presented to the presenter. And this session is being recorded and will be available for display and replay on AIST's website. Photos or recording of presentations is prohibited, and technical difficulties should be sent through the email system at the following address: training@aist.org. We have 2 standard guidelines that we practice at every meeting: an antitrust guideline. Each of these statements are in place to continue a session that adheres to the United States antitrust laws. We also have an anti-harassment policy, which is in place to make the meeting and teleconference comfortable for every attendee. I'd like to take a moment to introduce our moderators. We have 2, David and Felix. Felix has an educational background from the RWTH Aachen University in Germany, achieving the BSCE, Master's and PhD. And his career spans assignments with Le Hoist in Belgium from 2014 to 2021 as a project manager and lab manager. And he is currently now working with Badisch Stahl Engineering in Germany. He has a passion for decarbonization, and his current role includes consultancy solutions for mini mills and integrated steel plants. For AIST, Felix has achieved membership in the AIST European member chapter, and he's currently the vice chair of the AIST Decarbonization Subcommittee. Our next moderator is David Marshall, who from an educational standpoint started in the UK at Teesside University with an electrical background, and eventually moved to Western Canada, achieving his MBA at Ivey in Western Canada, as well as a CMRP designation. In 1982, he moved from England to Sault Ste. Marie and began that Canadian operation with Bailey Hoogovens, with duties including electrical, automation, and various transfer assignments, and eventually rising to the Director and Chief Operating Officer, heading up a 300-plus person North American Danieli Chorus division of Hoogovens. At 2001, he left for Performance Improvement Incorporated, his own organization that specializes in refractory, environmental, global reliability, and process equipment improvements. I would like to turn over the presentation to our first moderator, David Marshall.
Thanks, Charlie, and a welcome to everybody. Good morning, good afternoon, and good evening. I understand we're all over the globe. I'd like to add another information statement to the AIST standard that in 3 years, we've seen a lot of evolution in the facts and figures that's presented and plans as they're made. So we should take a warning that anything looking forward is just an estimate or a prediction of the future. And we would suggest that you verify all information before you take any serious decisions on what is presented. This webinar is the latest in a series that we've done in the last 3 years. I think it's number 8 or 9. And we've addressed broad topics as well as very specific topics such as hydrogen injection into a blast furnace. But this is our first one dedicated to electrical steelmaking, and we hope it will be the first of many. We've got plans on all the fascinating topics that section of our industry is the transformation that they're undergoing. And our first presentation is Victoria Morton of Nucor. She will give an example of the planning that's gone into what our future will look like for the industry. Victoria began her career in 2010, working as an environmental consultant with a focus on industrial air permitting at Trinity Consultants in Baton Rouge, Louisiana. After a couple of years in consulting, she moved into the integrated steel industry and joined US Steel in Pittsburgh, PA as an environmental engineer. Over the next 5 years, she supported US Steel facilities with regulatory, permitting, and compliance efforts throughout the USA. In 2017, she made the transition to electrical steelmaking and joined Nucor Corporation as an environmental engineer at their corporate headquarters in Charlotte, North Carolina. In this role, she supported numerous facilities with various environmental activities, including regulatory reporting and permitting of all media such as air, water, and waste. And in 2019, she transferred to Nucor Steel Gallatin, that's sheet mill in Ghent, Kentucky. During her tenure at Gallatin, she was promoted to environmental supervisor. And after 3 years of that role, she returned to Charlotte, North Carolina to assist in the sustainability initiatives as an engineer for Nucor. She now focuses exclusively on Nucor's environmental sustainability program, including reporting and initiatives to reduce greenhouse gas emissions across Nucor. Victoria graduated from Carnegie Mellon University with a BS degree in civil engineering and later obtained a master's of both environmental management and engineering management from Duke University. So I'd like to turn the floor over to Victoria, please. Thanks, Charlie.
All right, thank you very much for the introduction. Hopefully it's showing the slideshow.
Yes, we see the slides very well.
All right, great, thank you. All right, so as already mentioned, good morning. I'm Victoria Morton, and I'm a sustainability engineer at Nucor Corporation. Nucor is the largest recycler and steel producer in North America and a leader in sustainability in the steel industry. So I'm excited to share our story with you today. So we're all here to talk about decarbonization, specifically in the EAF steelmaking process. So today I'm going to talk about some of the ways we can reduce our carbon emissions and the great strides we're making towards net zero emission steel. All right, so I'm going to start with a brief background on Nucor. We have 3 major big business segments: raw materials, where we acquire and produce the raw materials that are used by our steel mills to produce bar, sheet, structural, and plate steel. These steel materials are then utilized by our steel products segment to produce various products, including wire, grating, joist, decking, metal buildings, tubular products, insulated metal panels, garage doors, and steel transmission towers, to name a few. Part of why I'm starting with our general business units is to get you thinking about supply chains and upstream and downstream manufacturing processes in general. Keep in mind that the elements of your manufacturing supply chain that you control can help with your implementation of decarbonization efforts. But before we get into that, let's start with the basics. So an important part of evaluating your carbon footprint is to start with quantification of scope 1, scope 2, and scope 3 emissions. My slide describes Nucor specific examples of our scope 1, 2, and 3 emissions, but I will start with the very basic definitions. Scope 1 emissions are the emissions from your manufacturing processes and business activities that are directly under your control. For us, examples include fuel combustion emissions and consumption of materials such as lime and electrodes. In terms of steel carbon emission reductions, we have opportunities to reduce via efficiency improvements and the iron unit mix. Scope 2 is the simplest to calculate because it represents emissions from the electrical grid that your company consumed for business operations from your local grid. Keep in mind that the contract you negotiate with your local utility, for example, using market-based factors, can improve your carbon impacts. This is one of the methods that Nucor uses to help encourage the general greening of our local utility providers. If you're interested in learning more about the electricity grid carbon impact in your area, you can visit the EPA's eGrid website, which stands for Emissions and Generation Resource Integrated Database. There is also the opportunity to support renewable energy through virtual power purchase agreements and behind the meter options such as on-site solar power generation. Scope 3 is perhaps the simplest to explain, but the most complicated to derive because it is all the other emissions from both upstream and downstream processes used by your company. So this includes emissions that are caused by others producing the materials that we consume in our manufacturing process. So that would be examples such as lime, electrodes, and gases. It also includes inbound and outbound transportation of these materials. So in terms of large-scale steel manufacturing, the largest potential scope 3 reductions can be seen from reductions in raw material manufacturing impact. We are actively investigating ways to reduce our greenhouse gas emissions through research and development and investment. But it's important to observe that EAF steelmaking already has a much lower carbon footprint than traditional extractive steel manufacturing. Our greenhouse gas intensity, including scope 3, is only 1/3 of extractive steelmaking and 40% of the overall global average. Keep in mind that the Paris Agreement and industry standards currently exclude scope 3 emissions, but we are still exploring carbon capture for DRI and using renewable resources to replace pig iron. We continue to explore opportunities to reduce our carbon footprint in terms of all the scope emissions, and we are going to review multiple examples today. So here are a few examples of the carbon reduction opportunities that we are evaluating here at Nucor. This is obviously not an all-inclusive list, but it demonstrates the opportunities we have to impact carbon emissions from all scope emission types. As discussed previously, we have many opportunities to reduce all our scope emissions. There are opportunities during the steel manufacturing process, including considering the source of electricity being used, in addition to impacting emissions in the upstream products manufacturing processes. We will start by discussing opportunities during the steel manufacturing process with the use of biocarbon. So biocarbon can be produced from sawmill residuals or sustainable forestry byproducts. Kyle is going to go into more detail into the EAF steel manufacturing process later on, but injection carbon sources are essential for foamy slag practices. So we are testing the substitution of fossil carbon in our EAFs with biocarbon. This reduces our scope 1 emissions, and if biocarbon is sustainably sourced, it is treated as zero emissions in most carbon accounting platforms. Another way we are looking to reduce our carbon emissions is via green pig iron. To give you a quick background, pig iron is a high-quality raw material that is required for the EAF steelmaking process. It's traditionally manufactured in a blast furnace using coke, which is derived from coal, contributing to a high carbon impact. Green pig iron is produced without the use of coal, which has obvious benefits in reduction in carbon emissions. In this process, iron ore and sustainable charcoal, which is produced from eucalyptus forest and is similar to biocarbon, are used to produce pig iron in mini blast furnaces. So this product gives us an opportunity to reduce our Scope 3 carbon emissions from the pig iron manufacturing process. Now we're going to talk about carbon capture and storage, or CCS. Now, most of us know there are many technologies being developed in this field. So I'm just going to provide the general concept for our purposes and not go into too much detail. So carbon capture, the essence is you are capturing carbon emissions from a manufacturing exhaust stream and adjusting the chemical properties so that the carbon can be transported to and stored in a permanent storage destination. Nucor has started our evaluation of carbon capture and storage at one of our DRI facilities. This is because the DRI manufacturing process provides a more concentrated carbon dioxide emission source, which makes current CCS technologies more feasible to use. However, the EAF steel manufacturing process doesn't provide as concentrated of a carbon emission stream. So current technology doesn't give us the same opportunity to capture that carbon. But we continue to support evaluations of new technologies to see if carbon capture could be doable during steel manufacturing. For example, Nucor has partnered with the University of Kentucky to conduct research funded by the US Department of Energy. The UK Center for Applied Energy Research is developing a carbon capture system to remove carbon dioxide from fossil fuel combustion. UK reached out to Nucor Steel Gallatin to request the mill test whether the technology could remove carbon dioxide from EAF stack gas. This will be the first time this technology will be trialed to remove carbon dioxide from an EAF stack gas stream, and Nucor Steel Gallatin is collaborating on the project to see if this CCS technology can be cost-effective at steel mills. So obviously still at the pilot stage, but it may be a future potential capture option. So we've talked about Scope 1 and Scope 3 reduction opportunities so far. So now we are going to tackle Scope 2 emissions. As mentioned previously, one of the simplest ways to support greening of the power grid is to participate in wind and solar virtual power purchase agreements. These agreements allow you to purchase renewable energy certificates, or RECs, one REC being equal to 1 megawatt hour of renewable energy. There are also opportunities for on-site generation of renewable energy with behind-the-meter generation and storage. For example, our Volcraft plant in Chemung, New York, has installed a 2.2 megawatt DC roof mount solar power system with roughly 4,000 solar panels. There are also opportunities for carbon-free emissions with nuclear power. So Nucor has invested $15 million in NuScale Power. They are a developer of small modular reactor nuclear plants, and their reactor design is the first of its kind approved in the US by the Nuclear Regulatory Commission. We are going to end our technology discussions with zero emission iron, which has significant potential to reduce our Scope 3 emissions. Nucor is evaluating novel iron making processes that could result in near zero emissions iron production. One of those technologies is being developed by Electra, which Nucor has invested in. Excuse me. The process involves electrochemical refinement of low-grade iron ore into high-purity iron. This low-emissions iron can then be used as direct feedstock in the EAF steelmaking process. Ooh. So sorry. All right. So in addition to supporting specific technology development, we have to make company goals that align with sustainability and a lower carbon future. In general, Nucor already is leading the way in sustainable steel making via our much lower greenhouse gas intensity. But we have also gone beyond our current industry-leading performance and have committed to an additional 35% combined reduction in our Scope 1 and Scope 2 greenhouse gas intensity by 2030. Please keep in mind that transparency and sharing information is a key element to reducing carbon emissions. So that's why we continue to publicly disclose and reduce our Scope 1, Scope 2, and significant Scope 3 greenhouse gas emissions. And we will continue to lead the charge. And beyond 2030, we are committed to reducing our greenhouse gas emissions with the ambition of net zero emission steel. And it's with technologies such as the ones we've covered today that are going to help us as an industry achieve that goal. So thanks so much for sharing your time with me today to talk about this very important topic.
Thank you so much, Victoria, for this very interesting and great presentation from you and from Nucor. There's very much good stuff in there, and we have a few questions from the audience. And also ourselves, we prepared a few questions. So I will start with the first question. As you explained, the EAF has come a long way since the early days of low-cost long products and can now make sophisticated high-grade flat and long products. How does this ever-increased product quality demand challenge the carbon reduction protocols you presented?
Well, it's a great question. And as my presentation demonstrated, EAFs are already capable of achieving significantly lower carbon emissions than our integrated competitors while still producing high quality products. But as product demand goes up alongside our desire to reduce carbon emissions, this pushes us to further support the development and use of technologies such as the zero emission iron technologies discussed that will allow us to increase quality while decreasing carbon emissions. So carbon reduction protocols require us to get more creative as an industry, but I think the technologies being developed will allow us to reduce emissions even as product quality continues to increase.
Okay, so I understand you're right. In order to reach the same product quality, we need those iron units, and it can be this pig iron as well, but has to be this pig iron as well. So, which brings me to another question, which reads, pig iron is a very valuable iron unit for the EAF. Does Nucor intend to purchase pig iron and later green pig iron? If yes, where? Or does Nucor intend to produce pig iron yourself?
Well, I'd say this is more of a to be determined question, but obviously we are considering a lot of approaches to reduce the carbon impacts of pig iron. So I do expect that purchasing green pig iron will be part of our decarbonization efforts. But keep in mind, we also invested in Electra and other emission iron technologies, zero emission iron technologies, and they will hopefully provide a lower emission pig iron option. So we are not producing pig iron ourselves, but we are supporting the technologies that will allow us to purchase lower carbon pig iron in the future.
Mm-hmm. Yeah, especially to not let the Scope 3 emissions then just blow off with a better EAF process maybe, but to purchase these emissions. Yeah, I understand. Thank you. So the next question we have is from Alexander Zeitlein. Hopefully I read this correct. He says, the EAF off gas is only 1% of CO2. Does it make sense to capture it? There's no cost-effective technology to do it, he says.
Right. Well, and that's why I say I brought up our UK technology example, but that's part of why I mentioned it's a very pilot process from our perspective. We want to support the research to make sure it isn't viable at this point. But yes, that is part of why I view it that we are trying to participate. Is it may work at the stage with higher concentration streams, but it's not guaranteed to work at the low amount we have. But the Department of Energy obviously wants to do research and confirm that. So, you know, we're helping support those efforts.
Okay. And then here's another interesting question from Dominic Paul O'Shaughnessy. And he says, how are in-house and purchased scrap treated as Scope 1, 2, or 3 emissions?
Sorry, can you repeat?
Yes, so he's asking how you allocate the Scope 1, 2, and 3 emissions for in-house purchased scrap, in-house scrap, so recycled scrap.
Oh, well, in-house scrap would generically be scope 1. It's still a slightly complex question as far as there's still a bit breakdown there as far as like scope 3, let's say transport. So it's not necessarily a 50-50 split. We do consider some of our scrap emissions as part of scope 3, but it depends. You have to go into the details to properly split it out.
Yeah, there's really a problem to avoid double counting then of these emissions.
Yes, exactly.
Yes,
so.
which we don't need and want. Then there's a question from Benjamin Dewlitt, and he says, is there a carbon benefit to replace coke or coal with charcoal, which would be derived from tree displacement?
Well, I feel like that's a tricky one because I'm not the expert to answer, by the way, for this element, but you know, if trees are being specifically farmed and you know grown for those purposes, that's a bit different, right, than just going and you know not cutting down from a rainforest. So I would say some of the elements here, it becomes a question of where the materials are being maintained and what sustainable practices they have in place in general.
Okay, so this is done. And then there is a question from Joachim Lehner, who asked, can enough charcoal be produced from eucalyptus forests? Will this be really sustainable? So he's a little bit in doubt.
Yes, well, and some of these, I always say it's a piece of the puzzle, right? Like it is certainly not meant to suggest that is an answer to our problems. It is one of the options we have to, you know, move towards greener, lower carbon emissions. So I would generally agree that it certainly isn't meant to take over and fix the issues. It's just a portion of what we can do as an industry to assist.
Yes. Then a last question from Luciano Jelenich, and he said, what is the anticipated timing when Electra will become a commercial-sized operation? Do you have something which you could already disclose?
I'm sorry, I don't have that information.
Okay, no worries. Thank you very much. So Victoria, thank you very much. This was the time we had for the questions for you. So all the other questions then we have to answer in the Q&A or via email later then. So thank you very much, Victoria, for these great presentations and all the answers you provided to us.
Thank you.
Okay. And now we will, yes, for the next two presentations, we have a tech team of Mike Grant and Kale Vanova looking at various aspects of electrical steam making, bringing in both theoretical and practical aspects for complete picture for EAFs and SAFs actually. So I will start with Mike, but Mike cannot be with us today. He had an urgent and short notice commitment, professional commitment with his company, but we do not want to leave left him over. So Mike Grant, or Michael Grant, is the Global Technology Director for Steel Production, Markets and Energy Transition at Air Liquide, Large Industries WBL. Just a short word, Mike is working globally to lead Air Liquide's technical and long-term strategies geared towards the steel industry. And he was involved in many big projects, also, for example, injection of hydrogen into blast furnaces, etc. He himself has a long career in EAF steelmaking. That's why we're happy that he prepared the next presentation together with Kyle Vanover, who you can see on the screen. So Kyle Vanover, he's a hot mill product metallurgist at Steel Dynamics Flat Roll Group, Butler. And he is a metallurgist with 14 years of experience at Steel Dynamics and has worked in various departments, including the electrical arc furnaces, the secondary metallurgy, caster, and hot rolling mill. Kyle is recognized for his technical expertise, analytical skills, and creative problem-solving abilities, and has enjoyed the team atmosphere in all of their both departments. Kyle earned his master's in engineering from Purdue University. So, and the first presentation of Kyle, maybe can we see you already, Kyle? There you are. Okay, so the first presentation is actually the presentation Mike would have presented. And it's electrical, chemical, and carbon inputs into scrap preheating in EAF operations. And here we will be looking into a few aspects of those regarding future green steel reality with EAF-based steelmaking. So Carl, thank you very much for joining us, and the floor is yours.
Thank you, Felix. And I'm already kind of feeling a little nervous following Victoria. I'm naturally a engineer / metallurgist, so I think socially awkward and lacking good presentation skills generally follows with the whole being an engineer. So hopefully I can try and do a good enough job to follow her. And hopefully I can do a good enough job doing some justice to Mike's presentation. He put this together, so it's kind of interesting. I think we have some differences of opinions on a couple topics, which could make some good debates. So I'm presenting this as he made it to try and to make sure that I get some of his perspectives across and try and cover all the topics for him. So his is electrical, chemical, and carbon inputs into scrap preheating and EAF operations. And kind of to start his presentation out, some of the important aspects is kind of looking at, sorry, it's kind of like lagging. Okay. Felix, did I freeze?
You did not freeze the
Oh.
slides, maybe reshare those slides again.
Oh, there it goes. All right,
It works, perfect.
Next slide. So trying to get into his presentation a little bit, one of the important things to kind of look at and start thinking about is how much EAF by kind of the percentage of steel produced. This is as of 2020, and so kind of looking like the United States, we're looking at say 70%, places like China 10%. So there's a pretty big disparity in the percentages of EAF-based production versus I'm going to say more conventional, probably blast furnace type steelmaking methods. But the question is, where is this going? So some of the big stuff, looking at where we're going. So, the EAF industry in the United States would continue to build electric arc furnaces. There's really no new blast furnaces that I know of coming online. So even that, say 70% is going to probably 85%. Europe, obviously moving to increase their share of electric steelmaking over blast furnaces. Same thing in Japan, building a significant, or looking at building a significant number of electric arc furnaces in the future. And then the big question mark is always what's happening in China. And these are just estimates. Not to say any of this is 100% real, but I think it drives some of the idea of why do we need to be looking at things like alternative iron units, pig iron, scrap. They're all commodities that are needed for electric steelmaking. So it's kind of why is it an important topic, as well as the decarbonization aspect of all of our countries, companies looking at different ways to try and lower emissions at the same time as we still have to operate and produce steel, which is kind of why we're here and why we're trying to figure these things out. So from Mike's perspective of what are the advantages and disadvantages of using direct reduced iron DRI, one of the the big aspects of it, this kind of depends on the output of what your plant is producing. But if you're trying to make, like I work at a flat roll mill, so we're making sheet products, flat products. So having clean steel is kind of important to us. It's not like making rebar or something like that, where you can have a relatively high residual content. So being able to use DRI with a low residual content can help clean up your scrap mix. It also allows you to somewhat use alternative cheaper scraps. If you have more DRI in your mix, that's a lower residual content. You have the ability to potentially increase some of your higher residual scraps in exchange that might be more economically priced. You can, with that lower residual mix, produce higher quality grades of steel because you can have lower residual contents. And that will maybe help if there's undersupply of scrap in the future as well, that DRI can make up some of those shortfalls. If there isn't enough scrap to supply, say, every country's needs, maybe some countries generate more scrap than others, or some countries are net importers of scrap or net exporters of scrap, the DRI can help make up some of those gaps. Challenges with DRI, depending on how the DRI is produced, can have a low carbon content, and it can also have low metallization. Depending on how DRI is handled, it can become reactive. It can start to actually reoxidize before it goes into the electric arc furnace, which presents challenges for the EAF. You have to add more fluxes, add more some type of carbon unit to do some type of reduction. If you have a low metallization, high FeO content, EAF shops with high productivity may suffer some downfalls of lower productivity because you're trying to reduce oxides in a oxidizing environment, which is energy intensive and kind of counterintuitive. If DRI, could help be cost savings, cheaper scrap. So So looking at kind of what the makeup of what DRI HBI is, kind of looking total iron content, 87 to 94%, but generally that's not all metallic iron. So we're talking about metallization and metallic iron. So metallic iron, probably 83 to 88%. And this will vary wherever you go and how close you are, and to maybe how close you are to where the DRI was produced, like time frame, how long it sat around, things like that. So as it sits around longer, it, depending on the environment it's stored in, can begin to react a little bit. So you always end up with some FeO, depending on how it's produced, where it's produced, carbon between 0 and 4.5%, some amount of phosphorus generally. If it's coal-based, you're going to have a higher phosphorus and generally probably a higher sulfur, where if it's more gas-based, you'll probably end up with lower phosphorus, lower sulfur content. You'll end up with some silica, alumina. So, and it has a relatively low basicity. So in an electric steelmaking environment, you'll have to offset this basicity with lime in order to make a foamy slag. So once again, talking about the basicity and the gangue materials, those gangue materials like silica that come along with the DRI require lime. Lime requires energy. So it influences the heat requirement for the process. You have to add more energy in order to melt those and flux those limes, and to get those fluxes or the gangue material into the slag. Proportion of FeO and DRI, or FeO and DRI HBI product. So the reduction of FeO in electric arc furnaces consumes a significant amount of energy. He uses the term heat. Can reduce yield. So as you add fluxes to the electric arc furnace, imagine that as basically a big sponge, and pretend it's somewhere between 33 and 37% FeO by weight. If you have to add more lime, make more, say, apologies for using imperial units, but say how many pounds per ton, or say even kilograms per ton of slag that you produce. If you have to add more lime, you make more slag. And if it's 35% FeO, having more slag means that you lose more yield, and you use more energy to do that. So there are disadvantages. Productivity will decrease, which is some of the slides to follow, or some kind of charts. So this is kind of looking at a first mass balance. So this is looking, I'm going to call it a no DRI, 100% scrap charge with, like, say, a 10% merchant pig iron. And so he's just trying to show a mass balance here, where all of your energy is going, what type of energies there are. So in this scenario, there's 45% of the energy is chemical. So that you're getting energy from the pig iron, you're getting energy from the carbons, the coals that you're adding to the furnace. And the electrical input here is 450 kilowatt hours per ton. So that's going to kind of contrast the following model, which is going to be more of a DRI type scenario. So this is kind of a chart showing a few different basically arrangements of scrap, cold DRI, hot DRI, and different metallizations of DRI. So using this as kind of like the base of where historical electric arc furnaces might be operating at, say, 450 kilowatt hours per ton. You're looking at a 100-ton furnace, power on time 58 minutes for this example, and making 1,800 tons a day. So if you're adding cold DRI to the furnace with a low metallization, you're seeing a fairly significant increase in electrical energy. You're seeing an increase in power on time and a decrease in productivity. And you can see the same scenario, but slightly better for cold DRI with a higher metallization. So metallization is key when looking at alternative iron units, or really any iron units that you're putting into an electric arc furnace. So here's an example of hot charging. So when you're hot charging, you get the benefits of all that extra thermal energy that's still from producing or reducing the DRI and making pellets. So in this scenario, even hot charging with a high metallization, you're now outperforming the scrap-based system by this model, using less energy. Obviously, there was energy put into the system when you were making the DRI, which isn't being shown for the electric arc furnace side here. But your productivity is increasing, your electrical energy is decreasing, and your power on time is decreasing. And here's kind of a model showing cold DRI with a 97% metallization. So this is a little higher, but really in the end, you can kind of see that the electrical on the previous one showing the 10% pig and scrap was a 450 kilowatt hours, but now you're looking at 502 kilowatt hours per ton. And only in this case, 35% of the input energy is chemical. You have, I believe that this was modeled using a slightly lower carbon content of a DRI pellet. So hot charging, these are some of his conclusions, that hot charging DRI is necessary to recover productivity. The proportion of FeO in the DRI is kind of important for looking at output of the electric arc furnaces. If you have high oxygen content, it will reduce your yield. So, the quality of the DRI plays a significant role on the electric arc furnace. And then once again, this is, that same chart, and really, he's trying to point at saying that DRI made with a gas-based hydrogen process with kind of a 94% metallization, but has no carbon, still requires a higher energy input. You're looking at a slightly reduced productivity, output of the facility, longer power on time. So, it's still looking at, say, cold charged. So this is kind of an output looking at CO2 data, or CO2 emissions. So this is the some numbers on what a blast furnace, so kilograms per ton of steel, CO2 emissions for a blast furnace BOF operation, and he came up with 1,540 kilograms per ton. Looking at EAF based, you see a 92% reduction in that. I guess some of the debates come in, at least that I've been involved with, at some point that scrap had to be some type of reduction to iron ore had to take place to make scrap to go into electric arc furnace. So then you get into the whole scope 1, scope 2, scope 3 talks. The 75% DRI, this is natural gas based. So you still, you still have some CO2 emissions, but significantly less, say half, I know it's 58%, but half of the blast furnace. And then using green hydrogen, you still have some level of CO2 emissions, but significantly less than that of the blast furnace. This is kind of just a, summary in the end that the low carbon DRI melted and refined electric arc furnaces, that you still are going to need injection carbon. You still have to have foamy slag, an electric arc furnace. There might be alternative means in the future for foaming our slag, like the biocarbons, things like that that are coming around. But largely, you'll need some type of carbon units going into that slag in order to get it to foam. So yeah, that was Mike's slide. I don't know, Felix, do we have any questions? Did I get through that quick enough?
Hey, Kyle. Yes, we have questions. We have quite a few. So first, let me start with some of those broad questions, and then we will go to a few more detailed questions. But first, you did very well with Mike's presentation. Nice job. It's really awkward to present from someone else, and you did well. So the first broad question is, how easy is it to switch the raw materials and inputs as the market prices and availabilities for all these commodities change, both long and short term? And then maybe I add one example, which is more specific, which you might like. So for example, Mike was talking about 100% scrap furnace with 10% pig iron in it. So for example, if we do a switch from 10% pig to 10% DRI, this could be maybe one example which makes the whole thing easier. So maybe let's first look at the overall thing, raw materials, inputs, market prices, availabilities, and then you could look into this specific example.
So for electric arc furnaces, one of the greatest advantages I feel from my experience with them is their flexibility in what types of raw materials you can put into them and how quickly you can change between them. With the electric arc furnaces, I mean, literally we can have, say, 6 or 8 scrap mixes out at our scrap bay where they could load and change from heat to heat to heat, depending on what type of product you're producing and the type of residuals that are required in the steel, or even, say, the availabilities of certain scraps. So as prime scraps become more difficult to acquire, if you're making grades that maybe don't require as high or as low of a residual content as other grades or material specs, then our ability to switch between high residual scraps to low residual scraps is one big advantage of the electric arc furnaces. The disadvantage is trying to make sure that at the same time you're balancing your fluxes and your carbon inputs to if you put in generally a lower grade scrap, it'll come along with, I'm going to call more dirt or more silica, more acids that will end up in your slag that you have to balance using things like lime and dolomite in order to try and protect the refractories in your furnace, in order to make a foamy slag, to make sure that you're getting the phosphorus out of your steel, make sure you're, doing a good job processing the steel at the EAF, doing all the things that you're supposed to do, and removing the other residuals in there, which you can remove, and making a good foamy slag that protects the arc, protects the furnace, keeps heat transferring to the bath, removing nitrogen, all those good things that we're trying to do in the electric arc furnace. So there's a lot of flexibility there. And that's one of to me, their biggest strengths.
So you're saying it doesn't, so there are these changes, these big fluctuations on availabilities and prices, and the EAF is just very suitable in addressing those because of the flexibility of the EAF.
Yes.
Would this be okay? That would be okay, great. And so this maybe already answers the second question as well. So each region of the world has a very different condition for raw materials and energy sources. So does this mean each region will develop its own particular electrical steelmaking process?
I think we already see that. As you travel around, you'll find different places are using different makeups of different carbon inputs, different scrap inputs, different, say, pig iron versus DRI, HBI. I think even like company availability, not even region, take like Steel Dynamics versus Nucor, for example. I know that Victoria, I'm not really letting her defend herself, but Steel Dynamics doesn't have a DRI producing facility. We might buy HBI on the market. We might buy merchant pig iron on the market, which has become more complicated based on world conditions. But trying to play in the global market is always a challenge, and the flexibility of the electric arc furnace, I think, gives some advantages that as long as you can get enough metallic inputs, iron bearing products to put in there, and as long as you're not trying to do too much reduction of ores in the electric arc furnace, it can be successful in many regions, and a lot of the same principles and theories apply. So as long as you have a good understanding of how to make slag and how to make steel, I think the electric arc furnace can work in almost any environment. Some of the struggles come into availability of power, stuff like that. Electric arc furnaces are hungry beast when it comes to electrical demands. The blast furnace doesn't use anywhere near as much electricity as the electric arc furnace does, and especially when we start talking about things like green hydrogen. I'm not an expert on the calculations of how much energy it takes to basically, say, break water to make hydrogen. But I believe I saw a presentation even in the decarbonization committee the other day, where you start talking about the percentage of countries that you'll have to cover in solar panels in order to try, if you were going to use green energy, to try and, instead of using, say, coal or gas-based power plants in order to produce enough electricity to make green hydrogen, you start talking about covering percentages that are whole numbers of countries and solar panels, just make enough hydrogen to supply, to offset the steel industry. And it's kind of like, well, I don't know if that's ever going to happen or not, or what other alternative methods, whether it's nuclear or how we produce enough power. But, aside from the hydrogen, electric arc furnaces require a significant amount of electricity.
Yes, the other day in a meeting, in the decarb meeting, we just saw this one slide for a specific integrated plant. If it would switch to fully green hydrogen, green electricity, steelmaking was like 0.5% of the entire country's area, which would have to be covered by solar panels. So that's the demand. Hungry beast is a very nice term. So you mentioned something very nice, which is a bridge not only for the next presentation, but also for the next question, which we have. You said if we do not have to do too much reduction in the EAF. So I guess you're referring to the metallization degree of the DRI, to be used in the EAF. And so here we have a question from Jason Ontwistle. He said, how does DRI affect the yield of the mined materials? Any idea to the total yield effect from mine through the EAF if it has no carbon?
Well, I guess some of the complications there from like mine to EAF. So, I mean, I can't 100% talk on this as I don't produce DRI, but I have some read literature on it. And one of the big things that you have to consider is depending on where you're producing your DRI and shipping your ore to it, and Felix has dealt with blast furnace as well, and I know this is a big deal for them, but when you mine the ore out of the ground, say it's Fe2O3 or Fe3O4, say 30 some odd percent of the weight of that material is oxygen. And so if you count that as part of the yield as your ore, you're automatically only looking at a 60 some percent yield of the weight shipped from the mine to the DRI facility before ever making a pellet or making the DRI, because you have to drive off that oxygen. You have to reduce the oxygen, and that oxygen has mass, and so you're shipping that mass as part of the weight in like a rail car, a barge, a ship, whatever you're putting it in, that oxygen has mass. And so if you're counting that in your yield, you're only looking at 60 some percent to begin with. Beyond that, actually within like the DRI making process, you end up with some fines in your baghouse dust and things like that. And a lot of those are recuperated in different types of processes. So actually producing the DRI, driving off the oxygen is from my understanding, a fairly high yield process. I don't have an exact number on it, but in the upper 90s% is what I've kind of seen it published in some other people's papers, and reading. I don't know if I should say like reading, say, like Midrex materials or something like that, some of their advertisements, but I don't have any hands-on. We don't operate our own facility to produce DRI, but from an EAF standpoint, when you add something with a relatively low metallization or say somewhat of an FEO content to it, you'll for sure reduce some degree of FEO, but my experience is the bulk of that FEO will end up in your slag. It'll go out your slag door into a slag pot and you lose it. So as high of metallization material as you can add to the EAF will directly correlate to the yield of your liquid metal coming out of the EAF.
And then in this very regard, there's the next question from Austria, from Joachim Lehner. So with Jason, we ask about the FEO content then of this DRI metallization, and Joachim then asks, will a 100% H2 produced DRI be the right DRI, or will there always be some natural gas used for DRI production to achieve a minimum of carbon content in the DRI?
I think that's a really good question, and I don't know if we have the answer to that yet, but definitely one of the big complications with, I would say, a green hydrogen type DRI is basically has no carbon content to it. And so that's one of the big advantages when you look at the efficiencies of how you add carbon to the EAF. And when you say, look at the 10% merchant pig iron scrap example, since that carbon is already in solution in the merchant pig iron that we add to the electric arc furnaces, it's already some kind of iron carbide bond. That carbon is very efficient in getting into the bath and forming some CO bubbles and helping with the reaction of things like removing nitrogen, removing other contaminants within the scrap that's added to the EAF. So I can't say that you'll always have to have some type of natural gas, but you always have to have some way of performing some type of, or you have to form some type of CO bubbles in steelmaking. So whether you're using biocarbon or however you do that, one of the downfalls, and maybe other electric steelmaking producers have different experiences than I do, but adding things like, say, just going to the historical way of adding some type of charged carbon. I know here at our facility, we use like an anthracite coal. The efficiency or the recovery of that carbon is relatively low. Say we may only recover 15 to 20% of the charged carbon that we add by calculation by mass, and the rest of that burns up and goes out to the baghouse before it ever even has the opportunity to go into solution. And so you have to add a significant amount just to try and do some good. So
Yes.
It might require the inputs of different types of alternative carbon units to increase in proportion to how much, how low the carbon content of the DRI is.
And I think you said something very important. We always need certain bubbles. Usually it's CO bubbles for many aspects. So there will be a minimum CO2 emissions maybe to the EAF always in the future, even with low carbon DRI or no carbon DRI.
Right. So even if you're adding like that biocarbon or any of those things, it's still carbon. It's just from, say, a renewable resource or some type of something that was going to be landfilled anyway. It still has carbon in it. You still put that in an electric arc furnace, you're still going to make CO.
Yeah, so it's still the question, decarbonization or defossilization. Like we discussed at the last conference, ISTEC last year in Pittsburgh. So now we have 30 minutes left, and now it's time for your own presentation. The SDI Butler presentation. So this one now is the SAF and EAF, theoretical and actual operations based upon the SDI Butler case. Very, very interesting case, especially for the integrated males, for those people who joined us today. Floor is yours again.
Okay, well, appreciated the opportunity to present two slides or two presentations for you guys. Hopefully I can present this one slightly more confidently since I kind of put this one together. But one of the big notes going into this, so I work at Steel Dynamics in Butler, Indiana. We operate a flat roll steel mill. We have 2 SMS thin slab casters here. We operate 2 electric arc furnaces. They're both twin shell furnaces, so we kind of looks like we have 4 EAFs, but there's 2 transformers. But we also on site have a facility that we call Iron Dynamics, which operates a rotary hearth furnace and a submerged arc furnace in order to produce hot metal that we pour into our EAF. So in this presentation, I'm going to talk a little bit about oxidation reduction, talk a little bit about DRI, and then I'm going to try and go into a little bit about our specific facility, because I know some people are kind of looking at doing something maybe not similar. Maybe some people are looking at using submerged arc furnaces, but just thought I would try and present what we do here. So the crucial role of oxygen in steelmaking. So one of the things, even though we're talking about decarbonization, oxygen is required in steelmaking. The EAF is an oxidizing environment, and we use oxygen for energy. We use it for controlling things like dirts, inclusions, and things like that. So having, say, silicon Si in your some type of something that's ends up in the electric arc furnace, you add oxygen to it, it makes silica, it floats to your slag, it helps you remove those impurities. Basically, oxygen is extremely important to the steelmaking process, whether you're looking at a BOF, an EAF, both methods of production, oxygen is important. And this slide, I try and show the electric arc furnace, or not even that's just electric arc furnace, but basically the spiral here is an idea of kind of all of our different processes. And you could insert, not just blast furnace here, DRI production, HBI, all those types of things where you're basically going from an iron ore, an Fe2O3 and Fe3O4, and you're reducing it down to make something like pig iron or HBI, DRI, something like that. So this vertical line here, call this line oxidation. So you have a higher oxygen content here, lower oxygen content here. And the circle is basically the kind of the curly Q is the steelmaking process. So we start by reducing the ore to a very low oxygen content, say single ppm digits. And then we go into something like the EAF or the BOF where we raise it back up, maybe up to like 1,000 ppms of oxygen. And then we go back and we do some kind of secondary ladle metallurgy where we bring the oxygen content back down by killing the steel, using aluminum, silicon, something like that to end up at some kind of low oxygen content. And then because none of us are perfect, we end up with some reoxidation when we go to the caster, whether you pick it up from, siphoning in air as you're transporting steel from a ladle to a ton dish, from a ton dish to some type of mold, you pick up oxygen along the way and you end up at a final oxygen content. So, that's kind of the life cycle of oxygen and steelmaking. You start high and you end up kind of in the middle of everything that all the work and energy that you've put into it. And so I think that slide's kind of important for, it's kind of one simple slide and one simple curve where you can look at the entire process of the, steelmaking. Oxides and steelmaking. So once again, our oxidation in electric steelmaking. So oxygen gas, dissolved oxygen and FeO react with elements in the bath. And sorry again. I wish I had a way to silence my phone. So oxygen helps aid in foaming slag. It helps us along our process in the electric arc furnace. So when we're looking at oxidation electric arc furnace, we're looking at removing carbon, removing aluminum, removing silicon, titanium, calcium, manganese, phosphorus, all of these things in the bath. And I kind of have a list off the side of common oxides that you'll find in steelmaking process. And some of these are things that you'll find in the secondary ladle metallurgy. But a lot of the things when you're talking about like silica, alumina, CaO, all of these things are important when you're talking about slags and slag basicity. So you'll find those at the EAF, CO, CO2, find at the EAF. So that's kind of some of those items. Reduction in steel making. So this is removing the oxygen from the steel. So this is either talking about the DRI, blast furnaces, things like that. So this is just looking at the other side of it. This is going from the ores, or even we reduce oxygen at the LMF using aluminum, silicon, things like that. So in this case, looking at converting iron ore, some type of combination of FeO into metallic iron. Metallic iron is what you kind of want for the electric arc furnace. And then I have a couple slides following this showing the similarities in between a couple production methods of the DRI and blast furnace processes. So I know talking about blast furnaces necessarily is not the purpose of what we're going for here, but I think a lot of people have experience with blast furnaces. So it's kind of important to kind of show some of the reductions that are taking place in blast furnaces. And on my next slide, I show DRI. And if you look at the coal-based DRI production methods, you're going to find these exact same equations for what's taking place to produce the DRI, which is right here. But I think what a lot of us are kind of looking at and talking about for green hydrogen and decarbonization are more of these hydrogen-based processes. And you're going to find that you end up with a lot of the same method. If you look between carbon-based DRI, if you look between blast furnaces, you're going to end up with iron plus water instead of iron plus CO2. That's kind of the output. And then the different methods of producing, gas-based DRI, shaft-based, which I think is the most common method out there. Last I read, that's like 75% of the DRI that's made on Earth is by the shaft-based gas method. You have fluidized bed, rotary kiln, rotary hearth, different things like that. And natural gas, I'm sure most people know, is primarily methane, but you end up with some butane, ethane, and propane in there as well. So you can kind of put those, a little bit of carbon in there in some of these reactions as well. DRI benefits and challenges for the EAF. So this is one of my slides that kind of goes along with and maybe slightly contradicts some of the things that Mike said in the previous presentation. Benefits, if the DRI is fully reduced, you can get a fairly decent metallic yield out of it. Some of it has a fairly low iron content. So if you have a good metallization, you're using, fresh DRI that's arriving at the EAF, hasn't sat around a long time, you can say even get like 96, 97% recovery out of it with a little bit of carbon. That's about as good as you can ask for almost any scrap. Maybe not quite the same carbon content or energy benefit along with the electric arc furnace. Some of the other benefits are if it has a high metallization, low energy consumption, basically the quality of steel, the low residual content, the DRI quality. So metallization is a big deal if it's coal-based, sulfur and phosphorus, and then energy consumption. These are all concerns when talking about DRIs. In the end, how long does it take for me to melt it? What is the effect of my slag? How much energy does it take to melt it? Once again, higher slag volumes. So if you have to add lime in order to counterbalance, you have that. Increased power on time, and then material handling is always, if you have DRI, it's reactive. So some people have to keep it underneath some type of inert gas environment, nitrogen and argon storage or some type of CO2 blanket. What is an electric arc furnace? So an electric arc furnace, in this case, steelmaking largely uses electricity, chemical energy to melt raw materials. So large refractory line vessel, scrap is melted, heat generated from electric and chemical reactions. Foamy slag is hopefully created. It runs much more efficiently if you make foamy slag. and the slag helps you in your steelmaking process. So the benefits of the EAF and the steelmaking process, you end up with flexibility, recycling, efficiencies, and environmental sustainability. So, in all of these here, flexibility, you can really change your inputs relatively rapid in order to adjust to different grades or material specs that you're producing. Recycling steel, it's very highly recyclable as a scrap, going into the EAF. It's a great raw material to go in there. Efficiency, less energy required than some other steelmaking methods overall, because you aren't trying to go from, say, Fe2O3 or Fe3O4 to Fe, then like a blast furnace, you're cutting that out and you're already starting with scrap or some type of reduced iron product. Environmental sustainability. So once again, to Mike's slides, you have a fraction of the CO footprint as some other steelmaking processes. So a little bit about SDI specifically. Once again, we're running 2 Fuchs twin shell EBT electric arc furnaces. We're charging about 178 tons of scrap, and we're ending up with about 165 ton heat. And with a twin shell furnace, and we're an AC shop, we run a relatively small heel compared to some people. We're only running about a 20-ton heel. And that's more of a thermodynamic problem than anything else. With the twin shell, we aren't putting power on one of our shells for, say, 35-40 minutes. So if you have a really big heel in there, you have heat transfer that whole time, you lose a bunch of energy that you have to heat back up later. We end up using about 56 pounds of lime per heat. The bulk of that is through sidewall injection. We're using about 45 pounds per ton of dolo. Our lime, we're looking at about 11 pounds added to the charge buckets, 11 pounds per ton. We're using about 46 pounds per ton of like some type of charge carbon or some type of larger pieces of carbon that are going into the charge buckets, about 6 pounds per ton of injection carbon. We're running our furnaces at about 110 megawatts. We have 120 MVA AC transformers. We have 17 secondary voltage taps. We run between 766 and 1350 volts, which means we end up somewhere between, generally on average, 60 to 80,000 amps at any given time. Our power on time is 35 minutes. We're looking at, say, 2.4 pounds per ton of electrode consumption. Once again, that adds into your carbon, since our electrodes are graphite, which are carbon. With the hot metal, we end up somewhere around 320 kilowatt hours per ton. So our hot metal from our submerged arc furnace is only about 7% of our scrap mix. So it's not that large of a player in our scrap mix. So if you say 178 ton scrap charge, that includes that 178 includes about 15 tons of hot metal that we pour in. So it's a relatively small percentage. It's not like it's 20% of our mix or something. And then we're tapping our furnaces around 3,000 Fahrenheit, 1,000 ppm of oxygen. We make primarily low carbon goods here. So our iron dynamics facility, looking at our raw materials, briquetting, rotary hearth, our process flow map, so iron dynamics, looking at them, you have your iron oxide sources, which we use primarily recycled or materials that would have been in some type of oh, sorry, it looks like Felix might have a question. I will stop at the start of the IDI part.
Actually, the slide before.
Oh, the slide before.
Just as a reminder for those who are not very don't know EAFs too much. So this is a twin shell furnace, which already has its own advantages. Maybe you could just have a few words on this one, on the single bucket. What is twin shell? Okay. And yes, maybe at the end about the tapping temperature and the oxygen, just in general, just maybe a minute or something.
Yeah, no,
because at the end,
that's a good question. I'll use this slide real quick because it kind of has a little diagram of kind of what our twin shell looks like. So ignoring the rest of the slide, our electric arc furnaces, we have one electrode gantry for 2 shells. So our electrical power goes to one shell at a time, and we call it, our term that we use as a battery. So 2 shells with one set of electrodes as a battery. So we have 2 batteries, 2 transformers, 2 set of electrode gantries, 4 shells here at Butler. But this twin shell configuration, we melt on one side while on the other side, we tap the furnace, and then we do basically an inspection of the refractory before we add scrap back to it. We put our scrap into the furnace, we pour hot metal into it from a ladle, and then it's ready. So when this side's done melting, this side's fully charged up with scrap and ready to melt again. So that's the single bucket charge, is the idea that some steel shops, electric steel shops, as you're melting, you have to stop, pull the electrodes out, open the roof, basically break the arc, add another scrap bucket of scrap, and then come back in and start arcing again. There's a lot of papers out there that'll show the efficiencies that come along with single bucket charging, a significant kilowatt hours per ton reduction. When you open that furnace roof, you lose a significant amount of energy. It's just a big benefit overall. If when electric arc furnaces are single bucket charge, I think that's just kind of an industry term for where you get all of your scrap in the furnace before you start arcing the first time. So hopefully that's kind of what Felix was getting to for some questions on that, and I'm happy to answer some more when we get down to the bottom. I think I'm making fairly good time getting through these, so there should be plenty of time to talk about any of the specifics on this. For iron dynamics, for the raw materials, we use basically raw materials, looking at a mixing circuit, briquetting, rotary hearth furnace and RHF, submerged arc furnace and SAF, and tapping liquid pig iron and sending it to our EAF. So our process, we're using recycled iron ore products, our carbon sources, coals, binders, and lime for fluxing. So all of these raw materials eventually end up in a mixing circuit. We have to dry and grind the iron ore products. We dry and pulverize our carbon to get into the mixing circuit. Our binders are basically organic, sugars, things like that. And then lime all go into this mixing circuit. We make a briquette. I don't know if it's fairly standard to say our briquette going in to the RHF kind of looks, it's a little bit of a large, like water softener type salt. I don't know, the size of your thumb, something like that. It's not like as big as a charcoal briquette or anything like that. So it goes to the rotary hearth furnace for our initial reduction. It goes to the submerged arc furnace where more reduction occurs and melting, or then we tap the hot metal and send it to the electric arc furnace. This is actually a picture of them tapping the hot metal out of our SAF. So talking about our rotary hearth furnace, it's a fairly large furnace. It's 50 meters in diameter, 164 feet. It's donut shaped. So the steel or the pellets, get loaded in a kind of on a bed and kind of go around the furnace. It takes about 15 minutes. It's a gas-fired furnace. We're running it between 22 and 2300 Fahrenheit. We have 8 separate heating zones. That the gas and the coals are both performing reductions in the furnace. We call them green briquettes as they go in. They're basically kind of some form of DRI, even though it's not a true DRI because we have fluxes for the SAF in there as it comes out. So looking at the green briquette and the rotary hearth furnace, it's not showing my animations very well, sorry. But the goal was to try and show that you have FeO, Fe2O3, Fe3O4 in here. The CO drives off the oxygen, and hopefully you end up with primarily iron. It goes into the submerged arc furnace, which I think is what most people were primarily interested in. So our submerged arc furnace is top fed. The feed kind of melts down in there as we arc. We're using Soderberg electrodes, which are basically graphitized in place. You add, basically graphite pellets at the top or carbon pellets at the top, and they graphitize in place. You kind of feed down into there. It's a top feed system. Our atmosphere in the furnace is 90% CO. So that CO going to CO2 helps drive further reduction of the FeO in here. So the feed piles kind of melt down, and as the liquid level increases, once it reaches a certain point, we drill a tap hole into the side, we tap it into a ladle and send it over to the electric arc furnace in a ladle where we pick it up with a crane and pour it into the EAF. We're melting with 42 megawatts over here. I think that's, you know, kind of called out there. So our, oh, that went really fast. So when we tap our hot metal is coming out of the submerged arc furnace, 95 to 96% metallic iron in liquid form. It's between 3.8 and 4.5% carbon, between 1 and 1.5% silicon, and relatively low sulfur content. And these are pictures, you know, this is a high-speed camera picture of looking at the tap stream coming out of the SAF, it kind of going down the runner. That runner then feeds down into a ladle. We use the crest carrier to take it over to our electric arc furnaces where we pick it up with a charge crane and pour it into our EAFs. One quick note about using hot metal. This is kind of like a safety note. As you pour hot metal in the winter months, one thing that we do is what we call a bore and pour practice. So if the electric arc furnaces might have ice or snow or some type of you know, frozen water in the furnace, we'll put a couple megawatt hours of electricity into the electric arc furnace, then open the roof and pour liquid on it. Yes, that slows our process down a little bit, but we've had some bad scrap type explosions pouring hot metal onto scrap with ice in it. And so it's just for a safety precaution now that we don't do that anymore. Once it's below freezing, we pour our hot metal in on top of scrap that we already arced in on. But in the summer months, we pour our hot metal directly on our scrap without arcing on it. We use about 7% hot metal, and our hot metal on heats where we do use it saves us about 25 kilowatt hours per ton, and we use about 3 tons less per ton of injection carbon. And that's the end of what I had for that.
Nice, thank you very much, Kyle.
Yeah.
I think also this presentation was very interesting, especially for those integrated plants who are considering, should I buy or should I build now a new EAF or an SAF? And so my first question is also going in this direction. So also in connections to Victoria's the questions we asked to Victoria earlier. And if we have a high demand on quality or maybe productivity, should we target a SAF or can an EAF do the trick in all cases?
You know, that's kind of a difficult question because I think some of that comes down to what are your raw materials. You know, I think in a lot of cases it comes down to, I think we all have a lot of options. What type of raw materials do you have access to? How much scrap do you have access to? What type of ores do you have access to? Do you have access to pig iron? Does an SAF or an EAF fit in with your company's decarbonization goals more than other production methods, or does it fit the needs of certain countries are passing regulations more aggressively and faster than other countries? So I think that's kind of a complex question to look at it from a global scale. I mean, here at Butler, the SAF does provide us some benefits. I mean, it's not perfect. Some of the, you know, things I wish that it could do more of. I wish that we had the capacity of our SAF to make more hot metal than it makes. We only make about 280,000 tons of hot metal out of that furnace a year, and our steel plant produces about 3.3 million tons of steel. So my dream was that the SAF for us here was that it could make even more hot metal, and that would especially help us right now in the global situation. Having more pig iron that could be produced on site would be great.
So I have a question here from Didier Botte. Who asks, what is your Soderberg electrode consumption at SAF per ton of hot metal? And maybe I would like to expand that question if you could make a comparison. Soderberg electrode consumption per ton hot metal versus graphite electrode consumptions per ton steel in the EAF. Maybe the 2 megawatts you have in comparison, EAF and SAF, and also the tonnage per hour, because at the end this is the upscaling factor.
Right. So I don't have with me the exact numbers. I don't really track the SAF electrode consumption that closely. Apologies. I can try and get that information to AIST to share. I don't think there's any big secrets there. I know it's not anything substantial. Our electric arc furnaces are running about 2.4 pounds per ton of, we run 24-inch diameter electrodes on our electric arc furnace. So that's what we're consuming there. What was there was several questions there. I got electrode
It was
consumption.
3, the electrodes, the megawatts you have, and the tons per hour.
Okay, yeah. So our electrodes consumption, sorry, did that one. The tons per hour. So we're making about 60,000 pounds of liquid hot metal an hour, at least. So call it 30 tons. And then that's what we send over to the electric arc furnaces in a ladle. We usually put that in a single ladle, and then we pick it up and then we split it between 2 electric arc furnace shells. So we have cranes have scales and things like that on it. So you can pour about 15 tons in one furnace and then pour 15 tons in another furnace with a ladle. That kind of helps us with not, opening a tap hole in the SAF too often, that you can put 2 heats worth in one ladle and send it over. Also makes material handling a little bit easier. So that's kind of our output from our steel plant. We're making about 6.5 tons a minute is the last metric that I used. Sorry, that wasn't in an hour or whatever you were going for. We're 3.3 million tons of finished goods a year, 3.2 million tons finished goods a year, somewhere in there, depending on how you look at finished goods, whether it's off the hot mill or cold mill lines. So you have some yield losses, cutting heads and tails off coils and things like that when you go to our cold mill. So actually finished goods leaving the plants, it's less, say 3.2 million tons, but we produce say like 3.3 million tons of liquid out of our electric arc furnaces a year here. There was questions about power. So our electric arc furnaces, we have 2 120 MVA transformers for electric arc furnaces. So 240 megawatts of power there, where our submerged arc furnace is only 42 megawatts of power, and we aren't always running that at full power. So, it's a pretty substantial difference in power. Quite a bit of electricity needed for the EAFs. I know that we were talking a little bit before about power consumption at an EAF based shop. So I don't know how nuclear power plants are globally. Most of the nuclear power plants in the United States are 1 gigawatt reactors. They might have 1 to 4, 5, 6 reactors at a facility. But just our 2 electric arc furnaces are usually roughly using 25% of 1 nuclear reactor to melt steel, to put it in some type of perspective.
Okay, just looking at the time, we have 3 minutes left. So at least 2 questions. I would use the follow-up question from Didier. He asked, what is the diameter of the Soderberg electrodes you're having?
They're fairly large. I don't know, I kind of stood next to them one time when I was in the furnace. The trouble is you don't really raise them in and out. They're there. They aren't like electrodes in an electric arc furnace. I can get a number on that too, but they're probably about 1 meter in diameter. They're fairly big.
Okay, and then the next question I will combine. It's a question from, again, Joachim Lehner and Raimund Fritz, asking about dry HBI and dry DI. I'm merging those 2 questions. So how important is dry HBI compared to dry DI, and should HBI be stored under a roof, or is it not necessary because of the brain?
I think that depends on the quality of your DRI and your HBI. Well, the DRI, I would say, always needs to be kept dry. The ability for it to react is quite substantial. I think you can read different news articles out there about DRI reactions happening in different places. I might call it burning. I know that it's really not burning, but reacting, and even melting ships in half and things like that. So there's substantial safety material handling concerns with DRI. HBI kind of takes some of the porosity and the surface area away. I know on site that we store HBI. We don't have a roof to cover our HBI that we buy at Butler. And I know that our Columbus plant in Mississippi and our Sinton plant in Texas doesn't have any roof to store HBI under. I'm not going to say it's necessarily a bad idea. It's kind of maybe one of those try it. I know that we got a load of HBI one time that might have been of a lower quality that got rained on and began to react. And I'm going to say the pile caught on fire. It began reacting so aggressively that we had to let it kind of stop reacting before we used it. So I think some of it comes down to the quality of the HBI you receive.
Okay, and so there are a few more questions, which I hope you could be answering offline in writing, because we're already at a half hour. We have to finish this webinar now, and maybe David, you would like to find a few last words for this great webinar, which is already about to find its end.
Thank you, Felix. Thank you, Kyle. Thank you, Victoria. Brilliant presentations and great discussions. As we mentioned at the beginning, this is going to be the first in a series of webinars, and hopefully we'll have Kyle and Victoria back to go digging down into more detail and exploring more of the options on what the future might look like in decarbonisation of the electrical steelmaking process. So Charlie, if you could close us off.
My pleasure, David.
Thank you,
And
everybody.
again, thank you for our presenters. Excellent presentations. This last 90 minutes will be curated and stored on the website here under conference and expositions webinars, where you probably use to register. That will bring you to a screen that says these past webinars are available. AIST would like to point out that there's also a resource center where written technical papers are available, somewhere close to 10,000 entries at this point. We do want to thank you for attending the webinar. There are additional activities stored in the webinar area from 2 previous webinars recently happening, and we do expect that those people that are coming in person to see us all in Detroit in the second week of May. Thank you all for attending. Have a good afternoon, evening, and morning. Bye for now.